And then I can just export it over to YouTube. So, with some high quality videos that I make too. What's that?
At this point, you should just be an official YouTuber.
I should be, yes.
My favorite is still when Dr. Rock came in and we gave a heads up set them up because that was all recorded.
Is it all recording? Yeah. Awesome. That's excellent. I love it. Any questions at all before we get started on stuff? No? All right. So, want to do a little bit more stuff with sufficient statistics and how to find them. Talk about a theorem about how you know whether or not they are minimum variance statistics, and then get into, hopefully a little bit more, into the hypothesis testing side of things, and start talking about how do you choose your critical regions to determine whether or not you're going to reject a null hypothesis. So those are kind of the last topics that we're going to talk about for the semester, which is good since we got, a week left. All right, so let's look at, go back here and look at, this is an example out of your book. It's in section 10.7. It's problem number 10.7-4. I want to look at part B. I just want to take the function. The actual directions are to find the Rao-Kramer lower bound, but I want to just use the PDF. All right. So we've got the PDF of 1 over theta cubed x squared e to the minus x over theta. So remember we talked about the factorization theorem where if you can write the PDF as basically a product of the the factorization theorem involved the PDF for the joint distribution for your random sample. But basically you can split it into two parts, right? A part that had theta with no x's in it, the part that did have the theta and it looked like a composition, right? Where we had a function, basically a function of the statistic that we were looking at, and then we could say that that was sufficient, right? Well, there's another way to get at this, which is also what's referred to as exponential form or an exponential family. So we say that X is a member, of an exponential family if the PDF can be written in the following form. It's function of theta, no x's, function of x, no thetas, e to the negative function of theta, no x's, function of x, no thetas. And then, again, where the support of x doesn't depend on theta. Now, notice that the whole point of being an exponential family is that you can basically factor your PDF, your likelihood, or your joint PDF into the same pieces that we talked about before, right? And then notice that this part right here, where we've got the part of the theta that involves the x, this looks like the composition of this d of x part. And if we think about the joint PDF, we would multiply all of these together. It would add in your exponents, right? When you multiply, we would add the exponents. This would be a common factor because the x's would change in that case, right? Because you're doing the random sample. So you'd have this factored out times the sum of those things. So when you have an exponential family, the sum of the d of x functions is sufficient for theta. So this is why we like exponential families. Most of the PDFs that you come across will be exponential families. You may have to rewrite it as e to a log idea, but most of them end up being exponential families so that you can pick out the sufficient statistic quickly. So notice in the example that we have here, I'll rewrite it down below this. We had 1 over 2 theta cubed x squared e to the minus x over theta. Well, I can rewrite this exponent quickly as e to the minus 1 over theta times x, right? So this now fits our exponential family form.
So if you write the form you wrote yesterday, the phi times h of x, how would you write that?
We would, well, we would do the likelihood function first and just multiply them all together, right?
Yeah.
So we would have, for our purposes, what would we have? We would have the let's see. If we did that last time, we did 1 over 2 theta cubed, and that'd be to the nth power. We would have product of your x sub I squareds, and then you would have e to the minus 1 over theta times the sum of the x sub i's. Oops, sum of the x sub i's, right?
Yeah.
If I did that right. So when we have our factorization theorem again,
So h of x would just be the product of xi squared, and then d of x would be the...
mm-hmm. So the phi would be, you would take this part here and put it over with that.
Yeah, so what I don't understand is that it says the phi cannot be, phi depends on x1, x2 only to the d.
Right, so this part would be your h, and this would be your phi of the summation of x of I. Yeah, yeah. That's how it fits in there. So I would just, this part that has theta and no x's, I would just stick with the other part, and it doesn't matter because I'm not plugging anything in for x there. The only place where the x is getting plugged in is up here. So that's how it fits in. It's a little bit easier if it's already in exponential form, or you just rewrite it in exponential form by doing like an e to a log thing. You can see what the sufficient statistic has to be quickly. All right. So since this is an exponential form, the sum of x sub i's is going to be sufficient. So we see that the sum of the x sub i's is sufficient for theta. All right, so what we want to do is we want to try to figure out how to use the sufficient statistic to give us a minimum variance unbiased estimator of theta. Okay, so it turns out that if we have an exponential family, we get the sufficient part because it fits the factorization theorem. The next part that pops up is a harder theorem that we're not going to prove. That says that, go ahead.
So you split those two apart because you need something of theta and something of x times each other.
Yeah.
Okay.
Yep, that's right. So if if we take a one-to-one function, a one-to-one function, it needs to be differentiable. Oops. And I should say and. Phi is equal to h of theta. Then an unbiased estimator of this phi is a minimum variance unbiased estimator of phi. Oh, I'm sorry. I need to make sure that that an unbiased estimator of phi, I forgot the word, based on the sufficient statistic. Forgot some words. Sorry about that. Otherwise, it wasn't clear how that was going to connect to what we're doing. All right, so this is a lot of words. We're not going to prove this theorem. We're just going to use the theorem to help us figure out what the heck I'm talking about here. All right, so we just said that the sum of the x sub i's is sufficient for theta. Right? Okay? But I don't know necessarily just by looking at that how I'm supposed to estimate theta from the sum of the x sub i's. Okay? So what we need to do is try to figure out a way to do that, and in particular I need to make sure it's unbiased, and as soon as I make sure it's unbiased, then I automatically get that it's going to be a minimum variance one, provided that the transformation that we use is one-to-one. Okay? So here, the reason why we want one-to-one, of course, is because I'm trying to get this, I'm getting an unbiased estimator for this phi. I would do the inverse function for this h to get back to the theta, is the idea. Okay. So let's see how this works. This is our sufficient statistic, right? So let's first try to see how we can get an unbiased estimator for theta based on the sufficient statistic. Well, if I want to do that, I better figure out what the expected value of one of these things is. Okay, so we're going to first compute expected value of x. Now, for distributions that you already know something about, you know what the expected values are, right? Okay, so that wouldn't necessarily, but this one will have to do a little bit more work. So we would need to compute, of course, in this case, the integral from 0 to infinity of 1 over 2 theta cubed times x cubed, because I'd have x times the x squared, right? E to the minus x over theta, d theta. This seems like work for the computer more than for me, because I don't want to do integration by parts 3 times. Okay. Of course, I say that, and you know, things won't work right, because that's just par for the course this semester. It wasn't just this class or numerical. I had problems in my other stats class this morning.
Maybe it's you,
I think it might be me.
It's a common
It's operator error. All right, so still haven't figured out how to get infinity put in GeoGebra yet, so I'm just going to do the integral this way. We'll do, what was it, 1 over 2, I'm just going to call it b, so I don't have to type in theta each time, x cubed. To put e in GeoGebra, you want to use an Alt-E to the negative x over b. And that goes from, oh, I don't want, I just said I don't want to do that with bounds. Let me just delete the bounds. All right. So there it gave me the integral. Okay, so we would, the b is a constant for our purposes, right? We would distribute this e to the minus x over b through each of the 4 terms. Well, of course, as x goes to infinity, that goes to 0, correct? And it doesn't matter what the power of x is on any of those terms. All 4 of those terms will go to 0 as x goes to infinity. Okay? When we put in x equal to 0, those 3 terms die. So the only term that's left is that term, right? And we get 3b when we put in x equal to 0. So the expected value of theta here, going back over here, we would get 3 theta. Yes. That better be. Because I'm doing an expected value with respect to x. Yeah, it better be. Thank you. Tick marks reset next semester. All right, so if I then wanted to do the expected value of your sum of your x sub i's, what would you get?
Sum of the expected value.
You get the sum of the expected values, and each of them has an expected value of 3 theta, right? So this becomes 3n theta. All right. So we know that the sum of the x sub i's is sufficient for theta, but it certainly is not unbiased, right? We agree? What would we need to do to the statistic to make it unbiased? Yeah, divided by 3n, right? Okay, so now when we do 1 over 3n times the sum of the x sub i's is an unbiased estimator. That is not how you spell estimator. What did I just do? Right? Because we just divided out the constant that was in front. Okay? So this was our sufficient statistic. The function of the sufficient statistic here would be constant times statistic. Is that a one-to-one function? If I just take constant times something, is that one-to-one? I mean, as long as it's not 0. It's got 1-to-1, right? Because you're just doing the function f of x equals cx. It's just a line, right? Okay? So
what are we mapping? So when we define the function,
we're just defining it on, say, s, and we're just doing whatever that function, whatever that statistic happens to be. I just want to make sure that it's 1-to-1. So we could reciprocate it, you could cube it, you could do the log of it, those kinds of things. I don't want to square it, for example. I wouldn't want to square the statistic because I don't know where the numbers came from.
So we're mapping from this our sample space to whatever it goes to.
No, it's just mapping from. In this case, it wouldn't be mapping from the sample. It would be the sample space of the statistic you're computing. So it would be the set of all possible sums of the x's in this case.
Oh, okay.
Yeah. So we would be doing from the set of all possible sums, in this case, to the set of all possible means, or thirds of means. Yeah, so we're just we're just basically, if we think of the statistic as a random variable, we're just doing a transformation of the random variable and making sure that the transformation is 1-to-1.
But if you're taking just n sample x's, then wouldn't the sum be the same in each point, or do we just take randomly n again another random set of n random set of x's?
Well, we treat each of the pieces of the random sample as a random variable, so we're doing the sums of those random variables, which in itself is a transformation of, well, in that case, several random variables. But that gives us just basically a joint random variable, right?
Yeah.
So the statistic that we've computed is just a joint random variable. And then we're just doing a transformation of that random variable we just defined.
Okay.
And the idea is that when I do the transformation of that particular random variable, I know that inputs are uniquely determined by outputs and vice versa, so that I can work backward to what I started with. That's the whole point of making sure that we're 1-to-1. Yeah. All right. So again, this is our statistic that we computed here. This is our function of that statistic. It's 1-to-1, and it's differentiable because it's just a linear function. So that theorem that I mentioned before guarantees that this particular one, so since the function f of x equals 1/3nx is 1-to-1 and differentiable, we know that, and well, I should say one more piece, and since the sum for x of I is sufficient for theta, 1/3n sum of the x of i's, or 1/3 x bar, is a minimum variance unbiased estimator for theta. So, just to reiterate, we started with exponential family. Wrote it this way, right? Once we have exponential family, whatever this part here is, the sum of the x of i's will be your sufficient statistic. So that's step 1.
So if that was like an x squared, it'd be some of the x y squared.
Yep. Yeah. Another common thing you'll see is logs here, because to write it as an exponential family, you'll do an e to a natural log. So then you'll see log xi there a lot. Okay. So that's first step, right? The second step then was to do the expected value for an individual one of these to figure out what the bias is, essentially, right? We did an individual one so that we could figure out the total and then figure out how we can adjust that constant. Does that make sense? Okay. So to give you another example here of how you might see something with an exponential family, my book gets flipped so far. This is 10.7, still 10.7-4, but part C. You've got f of x theta is 1/theta, x to the 1 minus theta over theta. Your x's go from 0 to 1, and your theta is between 0 and infinity. The way we would see that this is an exponential family is that I need to get this x. Since this x has thetas on it, I need to get this x in the exponent. To do that, we'll do the e to the natural log piece. So this would be 1/theta. I don't need to worry about that part because that's the part that's hanging out in front. Any x's that aren't attached to thetas can get stuck out in front too. It's the x's that are attached to thetas that have to be up in the exponent. Okay? So this is e to the natural log of x 1 minus theta over theta, or 1 over theta e to the 1 minus theta over theta, natural log of x. So here's your function of theta. Here's your function of x. Right? So now we've done that exponential form piece again. So what would be sufficient for theta? Good. Is that okay? So then what you would want to do next, I'm not going to take the time to do it because I was just flipping back over to GeoGebra again and using GeoGebra to get it. So now you want to compute the expected value of log of x.
So why do we want this? I think I missed it last time.
The reason we want this is because the expected value of this function will be in terms of theta.
Yeah.
And so we're trying to find a function of this thing that equals theta.
How to find the
Estimator. Right, to find the estimator. Right, that's why we're doing this part. So in this case, you would do integral from 0 to 1, because that was our support, of 1 over theta x to the 1 minus theta over theta log x dx. And again, use computer to do this. Use GeoGebra or whatever other computer algebra system you want. If you got a TI Inspire, you can use that. Yeah.
Do you want to listen to e to the maybe or the 1 minus theta, or is it?
I went back to the original PDF here.
Oh, okay.
Yeah. Because we're doing the expected value with respect to that original PDF. I mean, you could write it as e to the natural log of, but it's not going to make it any easier to integrate. The reason we did e to the natural log was so that we could see what the sufficient statistic was.
I was confused.
Yeah.
For some reason, I was thinking about the natural log.
Yeah, right. Yeah. Oh, it's down here. Yeah, it's down there. Yeah. Yep. Okay. So do this one, whatever that turns out to be. It'll be some function of theta. And so then you adjust it so that you get an unbiased estimator, and then that's your minimum variance unbiased estimator. That's the theorem is that once you find that the estimator, that's a one-to-one function of the sufficient statistic, it becomes a minimum variance unbiased estimator. Guaranteed. And it also turns out to be unique. It turns out it's the only one that has minimum variance. That is a much harder theorem for a much harder class. Like, for example, if you wanted to go get a master's degree in statistics, you would see the proof of that theorem.
Also,
Just as an example.
So we're always guaranteed that we find a one-to-one, just that constant function, multiplied constant function.
It depends on what the estimators turn out to be. And it might be reciprocation. That's another common one that flips up.
Yeah.
Yeah. So when you do your expected value, the theta ends up in the denominator. So you have to take a reciprocal. That's possible. It just depends on the problem. But the ones that you're going to do are all going to turn out to be one-to-one. Indifferentiable. That's the other important part. It's those pieces that make the proof of the theorem work. Well, at least I assume it does, since it makes those assumptions. I haven't actually looked up the proof of the theorem. I probably have a book that has it, but I didn't look it up because I knew I wasn't going to prove it, so I didn't care.
It's so deceptively simple.
Yeah.
Finding MVU is so easy. It's crazy.
It is crazy. I agree. It's weird. But I mean, I can understand why they need the derivative. I certainly can understand why they need one-to-one, because you're trying to recover information about the sample from the thing that you applied the function to. And if you can't if you can't recover that information because you've squared or whatever other types of things you could do to make it not 1-to-1, then you're not possibly going to have what you need. The differentiability, I'm sure, is working to do it, be able to do a transformation appropriately. Probably a Jacobian, I would guess. I'm just guessing. I don't really know. I haven't had enough of the higher level statistics to know, to have a feel for what the proof would have to go. But the fact that you're doing things which probably involve integrals, I'm guessing a Jacobian probably pops up. But that could be wrong. I could be way off. All right. Does that part make sense with finding the statistics? I mean, if you can show that it's an exponential family, finding the statistics is no sweat, right? Because it's just picking off the x piece. So being able to rewrite it in that fashion is what you want to do. All right. So let's change gears a bit and start going back to talking about hypothesis testing. So in particular, let's remind ourselves what we mean by the power of the hypothesis test again. So when you look at, let's just look at, say, a specific example here, maybe. So let's look at 10.2-1. This is on page 510. So this problem's about a potato farmer filling bags of potatoes, because of course it is. Okay. The farmer wants to fill up these bags of potatoes in the field, and the bags are supposed to hold 25 pounds of potatoes. All right. So let's suppose that this is normally distributed with mean, or with unknown mean, but variance 9. We're going to test the null hypothesis, which is that the mean really is 25, against the mean being less than 25. The farmer is underfilling the bags. All right. So in this example, we're going to do a random sample of 4. And we're going to let the critical region be, so C is going to denote our critical region here. And we're going to let this be, we're going to reject if the mean of the sample is less than or equal to the 22.5. All right, so when we do the power, the power idea is the probability that we actually reject the probability, of rejecting H0 when H1 is true, or HA is true. The book flips back and forth between HA and H1. It doesn't really matter. Alternative hypothesis. Remember that our probability of a type 2 error, remember type 2 error was not rejecting when you're supposed to? So this is the complement of that, right? This is rejecting when you're supposed to. Okay, so the power is 1 minus the probability of your type 2 error. Okay? We agree? All right. So we think about this in this particular case. The first part of this asks us to find what's referred to as the power function. The book uses K for power. The power function depends on what the mean is. Right? Now think about it. The alternative hypothesis here is that the mean is actually less than 25. Well, the lower that mean gets, the better chance you have of rejecting it, right? So the power should go up, because the lower that mean is, the less chance you have of making a type 2 error, not rejecting the way you're supposed to. Right? Do you agree? Okay. So, yeah, so how can we figure out what this power function is? Well, let's think about what would be the probability. So let's first just figure out what's the probability of accepting, I'll call it that way, accepting H naught when H1 is actually true. Now this is going to be in terms of, I don't know what mu is. This will just be in terms of whatever the mu is, right? How do you not, in this particular case, if this is your rejection region, this is when you're going to reject H naught. What's the chance that you don't reject H naught? What would you compute? Yeah, the X bar is greater than the 22.5, right? So I would need to do phi, this is a normal distribution, so phi is going to be involved, right? Right? So I want to compute the probability that you're above 22.5, right? Not rejecting when H naught is true, or not rejecting when HA is true, right? So I would need to do a z-score. That's actually the probability that we are less than 22.5, right? Right, so I would need to do 1 minus that. Oops, and then I didn't do the square root of my sample size. I forgot. So I need to put a 2 here, don't I? Because we're doing the mean of the sample. So I got to do the standard deviation of the sample mean, not the standard deviation of the whole population. We agree with that? I did it this way because this is how we typically think of problems, right? The probability of, you know, we have a mean, we want to know, okay, are we in a certain region? That's why I did it this way first. This is not power, this is just probability of making a type 2 error, right? So your power function then would be 1 minus this. So your power function, your k of mu, will be phi of 22.5 minus the mu over 3/2.
So this is power function, we just need to find how the probability is.
Yep, that's exactly right. Yep. So when we talk about the power function, that's why I did it in probability terms first, because we've done that, and then did the 1 minus afterwards. Right? So just thinking about how do you find the probability of making a type 2 error, right? This is type 2 error. And then power is 1 minus that. that's at least how I think about doing it. You should think about doing it the way that makes most sense to you, but that's the way that makes the most sense to me. Because we've already talked about how to find those other probabilities, right? And then just do 1 minus it because you're doing the complement. All right. So how does this... Notice that, of course, this power function is going to change based on what the mean is, right? We agree? The power function is going to change depending on the mean. So, of course, the lower the mean gets, the smaller this mean gets, the higher this probability is going to get. Right? Because this is cumulative probability up to a certain point, right? So the lower this mean gets, the highest this value gets, the better this power gets. And what we're going to be trying to do as we go through this stuff is how do we come up with the most powerful regions that we can, most powerful critical regions that we can, based on samples. Okay? So as we go along, we'll talk more about what we mean by that. I'm just trying to get the kind of the basics down first before we get into the more high-powered stuff later on. Okay. So the next part of this problem asks you, what's the significance level of the test? Well, significance level, again, is our alpha, right? The alpha assumes that what's the type 1 error again? That's the probability of making the type 1 error, so that's rejecting when you're not supposed to, right? So notice that if you plugged in 25 in for mu, that's exactly what that probability gives you, right? Right? That's exactly what that probability gives you. So your significance level here is the power function evaluated at 25. And you can use whatever means you want to use to figure that value out. Whatever that happens to be.
Don't we, isn't significance level is something that we introduce ourselves and not dependent on null?
Typically we introduce it ourselves, but we're going to want to make it, we want to try to make it an acceptable level for us as also an acceptable level of the other type of probability, the type 2 error part. So that's, we want to keep mindful of, well, okay, if we change the power, what happens to the significance level too?
Well, it's just surprising to me that we could find significant level just from the null hypothesis. I mean, the null hypothesis and the ultimate hypothesis.
Right, well, I mean, this is kind of given in a different way as we defined what the rejection region was first, and then that's what gave us the significance level. Usually we do it the other way around. We pick the significance level, and it gives us the rejection region. So we define significance here by saying what the rejection region was, and then from the rejection region we can determine what the significance level is.
Oh, you're right.
Yeah. We essentially did set the significance level. We just defined it by rejection region. But that's what we're going to be trying to do in general later on, is that we're going to try to pick rejection regions that give us the most powerful tests. And if we pick the rejection region, then that's going to tell us what the significance level is. So, yeah. I know it's a lot of kind of mind-bending stuff at this point because it's different than what we've talked about up until this point. I agree. It's hard. That's why I saved it for the end. Okay? All right. So this would be your significance level, and you would compute this just like you've done other things with computing it. Use a table, use your calculator, use Excel to get those values. Does that make sense? Okay. So when you're finding the power functions, in this particular, and these ones, it's I think all the ones that are in the book are all doing them relative to normal distributions, and then giving you sketching graphs of the power functions and stuff. Something find the values and sketching the graph of the power functions depending upon what the function looks like and those kinds of things. So I don't want to start the next thing because it's one of the bigger things that we do for this. So I think I'm going to stop. I'm sure you're going to really complain about that.
How dare you?
How dare you?